Hello, friends and students. We're here going to talk about power series, Taylor series, and Maclaurin series. My name is Haga, Augusto, Denari, Purba.
I'm Herbert, Tjong.
I'm Jasson Alexander Tanko.
I'm Putra, Mehendra, Kusuma,
And I'm Hariff Azis. Today we will cover 3 chapters, which are Power Series and its operations, Taylor and Maclaurin series, and the last one is Taylor approximation for functions.
The purpose of these topics are the power series are used to represent common functions and also to define new functions. A Maclaurin series is a power series that allows one to calculate an approximation of a function f of x for input values close to 0, given that one knows the values of the successive derivatives of the function at 0.
The power series is another type of infinite series or polynomial that diverges or converges based on the written theory below. There are actually several ways of solving this series. Some of them are hyperharmonic series, integral test, limit comparison test, ratio test, and root test. The first one, hyperharmonic series, or usually called P series, is where the P shows it convergent or divergent. The next one is the integral test, which decides its convergence or divergence based on the result of integrating, and the series has to be decreasing.
Limit comparison test. Limit comparison test is a test that uses the original formula and takes out the new formula, which doesn't contain any non-negative terms, and as well as removing any insignificant constants. The new formula is calculated as the limit of the original of the series formula over the new formula. To determine its convergence or divergence, you have to look towards the VK, which is the new formula, and decide it from there. Ratio test is a test of comparison as well. The difference is the ratio test makes a new formula by adding 1 towards the variable within the formula, then proceeds to calculate the limit as well. Root test is a test of series which only contains of positive terms, and it takes the original formula and its roots and root it with its variable, or in exponent term, you power the formula with 1 over the variable. So this is an example of the limit comparison test in which the original formula is 1 over 3 to the power of n minus n. The new formula is that I take out the negative n, and which proceeds that the bk is equals to 1 over 3n. After that, I take the limit, which is ak over bk, which is 1 over 3 to the power of n minus n, multiplied by 3n, 3 to the power of n. It gives the result of limit n to infinity, 1 minus n over 3 to the power of n. This results the 1 and the minus you remove, and then it becomes to 1 minus limit n to infinity, 1 over 3 to the power of n ln of 3. We get that from the L'Hopital, and it results in 0. So 1 minus 0 is 1. The 1 over 3 to the power of n is converging, so the whole series is convergent.
The next example is by using the integral test. Here we have 1 over n ln n, and the function that we're going to use is 1 over x ln x, that is by substituting n with x. The next step is by integrating this function, which we will have the result of infinite. The integral of this function is divergent, and so the series is also divergent by the integral test.
For the disturbance. Okay, now we are going to talk about the Taylor and Maclaurin series. Taylor series is one of the most important series in calculus, so let's talk about it. So Taylor series is basically an infinite sum of terms that are expressed in terms of the function derivative at a single point. So here is the formula of the Taylor series, which is n the factor of n. A is the real or complex number, and fn of A is the nth derivative of f evaluated at the point A. Okay, so from the equation before, we can write the fx as fa plus f the first differentiation of A to the divided by the 1 factorial, because it's the first, and times x minus the A. So since this is the equation is to the infinity and we are not certain, so we write it to the nth term. Now let's talk about the sample so we can understand it more. But before that, let's talk about the several frequent use Taylor series so we can work with the Taylor series even faster. Here are some of the samples. Okay, now we're going to talk about the sample. Is to make sure that everything is clear. First, the example is find the Taylor series of fx, which is the 1 over x plus 1, with A equal to 2 to infinity. First thing, we need to find the first differentiation, third and second, and to as many as possible. But it's normal that if we find it first, second, and third only. Then we put the x to A, so we get the f2, the first differentiation 2, and so on, and we get the result there for the differentiation. Now after that, we put it from the answer there, we change it into the Taylor series version, which is in the next slide. So then you just simply need to input to the formula which is stated before, and we get the result as you can see there.
So the next thing we're going to talk about is a Maclaurin series. Maclaurin series is a Taylor series expansion, but instead of using the x min minus A, we use 0 as the inside of the brackets. Okay, so here are some useful Maclaurin series which is frequently used. There are some e to the power of x, sin x, cos x, and sin hx, and many more. So here are the example of how to do the problem of the Maclaurin series. So here we need to determine the Maclaurin series for the function of x, root 1 plus x. So here is how you solve the problem, which you need to use the Taylor series, but instead of the x minus A, you use the 0.
Okay, so we have the Taylor approximation for functions. This is a form of approximation if we want to see the general value of a Taylor series. It's to represent a number as polynomial using Taylor series. Taylor series is an infinite sum of terms, and we use this when we want to look at different things that are harder to compute. And okay, so we use the quadratic Taylor polynomial. It's a form of the Taylor series formula. It's rewritten, and the steps are: we identify the function that resembles the number in the question. We choose a number that makes f of a equals to easy to compute, and select x so to the number that we are going to want to be approximated to. And the terms of n determines how close you want the approximation would be. Higher the number of n, the better the approximation would be. So this is the example question 1. Basically, we have the question is the Taylor series with function as such, f0 equals to 3, and we use the Taylor series formula to derive the first until the fourth derivatives. We can stop at the fourth derivative, as the fifth until infinity derivatives are 0. We then replace the first function with 0, and we find the results. We put them into the Taylor series polynomial formula, and so we have the last section down there as the approximation of the Taylor series itself. This is our second example question. It's from the Calculus Weber Purcell book. We approximate 0.9 using the first two terms of the Taylor series, or n equals to 2 based on a equals to 1 for the function of fx equals to ln x. We use again the Taylor series formula to find the first and second derivative of the Taylor series, and then we replace the x with a, which equals to the one on the middle, resulted in 1, 2 ones, and minus 1. We placed on the polynomial Taylor series formula, and then we get ln of 0.9 is equals to 0.1050, which is accurate to the fourth decimal place of the calculated value of ln 0.9, which is close enough, although it won't be as perfect as the calculated value. Thank you for watching our video. See you soon.